Hi, this is Emmett, and I'm presenting my Lab 4 on oscillation. In this lab, we're studying the energy principle, that being the change in energy of the system is equal to the work done on it by the surroundings. That means that if no work is done on the system, then the change in energy will be zero. We are also studying two-dimensional motion. To do so, we will track a video in Tracker and compare it to the computational model made using initial information found in Tracker. Here's my Tracker after it has been tracked. My video after it's been tracked. From this, we're given that the mass of the weight is 0.402, and the initial position is negative 0.131 meters in the x direction and negative 0.65 meters in the y direction. The initial velocity is 0. The spring constant is calculated to be 6.869 newtons per meter. The period is 1.52 seconds. The relaxed length of the spring is 0.1265 meters, and the start time 0 with the end time being 9.307. Using that data, we will plug that into formulas to find the force gravity, the force spring, the net force, and the kinetic energy, potential energy of the spring, and potential energy of gravity. And we'll combine that all together to find the total change in energy. Using the data found in Tracker, we input our values for mass, initial position, initial velocity, the spring constant, the length of the relaxed spring, and the end time seen here. Next, we move on to the calculations. We find the stretch of the string by taking the length of the string minus the relaxed length of the spring. And then we find the kinetic energy by doing 1/2 mv squared, like we talked about before. We find the potential gravitational energy by doing mgh. We find the potential spring energy by doing 1/2 times the spring constant times stretch squared. Next, moving on to the loop, we set the initial kinetic to equal to the prior kinetic energy, and we do the same with the two types of potential energies. That way we update it each time, and that'll come in useful and helpful. That'll be helpful later when we have to find the change in kinetic and potential energies. Here we calculate the gravitational, which is negative mg in the y direction, the spring force, which is negative times the negative of the spring constant times the stretch, and the net force is simply equal to the force of gravity plus the force of the spring. The ball's velocity is found by updating the previous ball's velocity by adding on the acceleration times the length of the time step. We find acceleration by doing the net force divided by the ball's mass. The ball's position we also update by taking the prior position of the ball and adding on the velocity of the ball by the length of the time, multiplied by the length of the time step. Here we once again find the stretch for inside the loop, and this is our visualization of it. Here we update our kinetic energy each time with the same formula, 1/2 mv squared, and do the same for the potential. And here we find the change in the kinetic and change in potentials by minusing the new kinetic energy from the initial kinetic energy. Finally, we put this into a graph using this, and also make a graph of the ball of the CSV file found in Tracker, so we can compare our computational and our experimental data. Here's my code being run. As you can see, the red ball, which represents our data in the CSV file, is slightly below the computational model. This is because I tracked the weight at the bottom of it because it was easier to be accurate with. So although it is not in the same position, it moves in the same manner. Here is a graph of our change in kinetic, change in potential energies. The blue line is the change in kinetic energy, the red line is the change in potential spring energy, and the green line is the change in potential gravitational energy. While the yellow line seen here is those three all added together, so that's the total energy. As you can see, it's equal to 0, so energy is conserved. Alright, here's my model being run again, but this time the graph is of the positions of the computational and the tracker motion. So once again, the red ball is below the blue computational model. However, the motion is pretty much the same. It follows along very well. Here are the discussion questions for today. For your model system, is the energy principle satisfied? As we talked about earlier, the total changes in energy added together equals 0, so yes, the energy principle is satisfied because energy is conserved. And 2, using the data you obtain in Tracker, make 2 separate estimates of the oscillation pyramids. One using the x position data, and the second using the y position data. Well, as you can see, these are my 2 period times found for the x and y axis. So you can see they're different, and this likely comes into play due to the z-axis not being accounted for. It would affect both of them differently and thus give you different times for your period. Thanks for listening along with me all today, and I hope you all learned something from this.